As the name says, computers is about computing, and so computer has some way to do calculations. A computer is making calculations using zeros and ones. These zeros and ones are called bits. Computer calculations are performed using logic. For example, the not operator will be able to change a 0 into a 1 and a 1 into a 0. There's 7 basic operations. And with these operations, more complex calculations can be made. Computers needs to have one way of having a physical representation of these zeros and ones. So how do we go from the zeros and ones to the actual computer? The zeros and ones, the bits of a computer, can be represented by a physical system that has 2 levels. So a computer consists of an electric circuit. This electric circuit has, for example, a basic flow, and if the flow is high, then that could be a 1. If the flow is low, it could be a 0. Or it could be that if there is a flow, then it's a 1, and if there is not a flow, it could be a 0. So there are different ways of doing so.
The kind of computers that we use today are based on classical physics. And classical physics is basically what we're actually used to every day. So all the things that we generally see are based on classical physics. I guess the idea of quantum computers is that you take advantage of these strange and different quantum mechanical laws that are out there and use that as sort of the fundamental of the computing device. The point of quantum computers is to actually do things that you can't do very well with with computers that you already have. The thing with quantum mechanics is that you can have things in 2 states at the same time. The example that people often give is that you can have things in sort of 2 positions at the same time. That's a kind of a bit of an artificial way of explaining it, but this kind of thing doesn't really happen on the human scale. But when you go to things which are on the microscopic scale, then this kind of thing can happen.
Superpositions, once anything interacts with them, it'll typically, the phrase that we use is collapse the wave function. But then what that means is that, so I've got this superposition, I've got like a 0 and a 1, and then I go through and I make a measurement, and it kind of becomes, one or the other. And so after that measurement, it's now 0 or 1.
The basic principle behind quantum computation is that quantum properties, instead of physical properties of a classical system, can be used to represent data and perform operation on this data. As for classical computers, information is coded with 2 levels of a physical system.
A qubit, this is basically a shorthand for a quantum bit. For a quantum bit, what you can have is it can be 0, it can be 1, but it can also be both 0 and 1 at the same time. So it can be in this superposition state of 0 and 1.
You could just have a computer made out of quantum bits. Examples would be photons, Bose-Einstein condensates, superconducting qubits, or just a trapped atom.
Atoms are composed of a nucleus at the center, surrounded by particles called electrons. The electrons occupy different orbitals that correspond to different energy levels. By choosing 2 energy levels, we can obtain a physical system with 2 levels that we can designate as 1 or 0. In this sense, atoms can be used as qubits. When we shine light on an atom, this light can be absorbed by an electron. In this case, the electron gains energy and goes to another orbital, for example from 1 to 0. Therefore, atoms can be used as a way to represent and manipulate information as zeros and ones.
You can send something to one level and then you can send it to the other level. And you could stop there. You could just have a computer made out of quantum bits that's a classical computer. And then we can push it further with something like superposition states.
The main picture that people give on why quantum computers are faster is that essentially you can do processing in a parallel way. For example, let's say you had a sort of a box which spat out a particular answer when you press the button, and you gave it some input value. if you put in 0, then it gave you some answer, and if you put in 1, then it gave you another answer. So if you wanted to find out what those two answers were, then you'd have to do it twice. But with the quantum computer, because you can put in basically 0 and 1 at the same time, then that means that you can get the two answers out at the same time.
As with classical logics, the operations performed on qubits are called logic gates. For example, the NOT gate also exists for quantum computers. Similarly to the classical case, it transforms a 0 into a 1 and a 1 into a 0.
Quantum gates are basically just any kind of manipulation that you can do on a qubit. So it takes it from some initial value and turns it into a final value. There are actually more operations that you can do because on a quantum bit or a qubit you can have not only the 0 or 1 but also this kind of superposition state. For example, you can take a bit which is initially in 0 and then you can turn it into a superposition of the 0 and 1. And this is a particular gate called the Hadamard gate.
This is useful for quantum computation, but like deceptively useful. All of these solutions are actually not information that you can get.
In quantum mechanics, measurement is actually quite a sort of a fundamental thing. When you have a particular quantum object and you try and measure it, you destroy the state in the process. And this is not something, like that you can improve. It's not like you can get a better measuring device. It's been shown that it's a kind of a fundamental nature of quantum mechanics. So that basically describes what this measurement problem is.
The biggest problem with quantum computing isn't doing the calculations. The work comes in getting the answer out of that. The way quantum computing works is that, these superpositions are really useful, but you have to make one superposition state come in with another one, and they interact in such a way that the answer you're looking for becomes more probable.
The tricky thing is to come up with a good combination of these gates so that you actually do something useful. When you combine a lot of these gates together, you call it a kind of a quantum algorithm. Any kind of program that we have on a computer is essentially just a kind of a certain algorithm in order to do a particular task.
And then you can also entangle qubits, like you can't do with classical bits. You can't entangle a classical bit.
In certain cases, several particles have to be described globally as a whole, and their properties cannot be described individually. In this case, the particles are said to be entangled.
The basic idea with entanglement is that you can sort of have two objects which usually have sort of interacted at some point. Even when you pull these particles apart, and then if you affect one of the particles, it kind of affects the other particle, and it does this in a kind of an instantaneous way.
You can't describe each object as well as you could describe the whole. And this is really strange, actually. The two objects are no longer kind of their own thing, in a way. One use of entanglement in quantum computing, or just quantum information in general, is this thing called quantum teleportation.
When you do teleportation, you transfer a kind of a state from one point to another point using this kind of entanglement. That's not really quantum computing, but you might be able to use it to transfer information, or maybe you might be able to do things like cryptography. The difficulty is actually making a large quantum computer. A small quantum computer people have already made.
The things that you have to fight are, the bigger your quantum object gets, the more susceptible it is to decoherence, so the more likely you're going to lose your entanglement, lose your superposition. You can do more with a quantum bit, but the trade-off is that they're a lot more sensitive. When it comes to making a qubit, there's really no limits. For instance, we're using Bose-Einstein condensate.
So what is a Bose-Einstein condensate? Let's imagine you have a jar of a certain type of gas. When you cool down this jar of atoms, and it's the right type of atom, so-called boson, what happens is that the atoms in the jar, they're essentially all stop moving all at the same time. And at this point, the atoms start to behave more quantum mechanically, and they all sort of sit on top of each other in this same type of state.
It is possible to design a quantum computer based on Bose-Einstein condensates by using the hyperfine levels of the atoms forming the Bose-Einstein condensate. Bose-Einstein condensates have been shown to have similar properties as standard qubits.
Even for a small Bose-Einstein condensate, you typically have over 1,000 atoms. This means you actually duplicate that information like 1,000 times. Even if you lose an atom here, or one gets corrupted, you've still got 999 left. It's a bit more robust because it involves a lot of particles.
Bose-Einstein condensates, it has a very special property that means that you get quantum nature on a macroscopic scale. So macroscopic meaning that whereas atoms are very small, a Bose-Einstein condensate can be relatively a lot larger.
For regular qubits, you can't actually read out that qubit very well. Even if you sort of had the ideal state, when you measure it, you actually kind of destroy the state in the process. With the Bose-Einstein condensate, because it involves a lot of particles, in fact you can actually read out that information. And so we think that means that this gives you a lot more options in terms of what you can probably do with a quantum computer. We're a group that researches quantum information. We think Bose-Einstein condensates are a good way of storing quantum information. We're a theory group. We use basically mathematics. We also use computer simulations, but we also work with sort of experimental groups.
My current project investigates different ways of doing single qubit gates. The way I do this is by investigating a particular kind of method for transferring information inside of, between different states in atoms. The idea is just to figure out ways of placing the atom in either state 1 or 0, and then transferring it back and forth between those states. That's the basic thing you have to do in order to build a quantum computer.
My current field of research involves algorithms. So an algorithm is basically a set procedure of calculations you do. So maybe a combination of logic gates to achieve some desired output. There's a phenomenon called quantum parallelism. If it's manipulated in the right way, we can increase the efficiency, as is the case with this quantum search algorithm, also known as Grover's algorithm. So basically, by using Bose-Einstein condensates, we can extend this small phenomena to a larger system.
The project I'm currently working on is about entangling two Bose-Einstein condensates. The method I'm investigating involves exciting the atoms to a very high energy level so that they can interact with each other, and then that creates the entanglement. The way we excite the Bose-Einstein condensates to this very high energy level is by shining light onto them. So what I'm looking at is which shape the pulse light should have and how long we should shine light onto the Bose-Einstein condensate.
What I specifically do is I look at measurements that actually doesn't destroy the state of quantum objects. Just imagine like a CD. You can always read it 10,000 times and it doesn't erase. But for a quantum object, it's not the same thing. After interaction, the state of the system has changed. I just store this data and each time I read it, it's gone, right? But what if you can do something that you build a huge data set and at least you can read it up to, let's say, maybe 20 times before it's finally gone? The type of interactions I look at is non-destructive interactions.
My project is a bit different from trying to build an actual computer, but it's still related to quantum computation. It's about trying to understand the role of quantum mechanics in living phenomena. We simulate some cells in a way that's, we can say, analogous to a quantum computer, and they can be half alive plus half dead, okay? Then according to some rules, those cells will interact, and these rules are the actual quantum computation.
My scheme consists on two entangled Bose-Einstein condensates, each one of them isolated in one single cavity, and we interact with each Bose-Einstein condensate through a laser beam in order to change its value from 0 to 1 and each given superposition of these values, and then Bose-Einstein condensates interacts between them with an optical fiber, and they send light to each other. This is how the entanglement is made.
My specific work is on entangling Bose-Einstein condensate qubits. The entanglement is done by placing the Bose-Einstein condensates in two cavities. We'll fire a laser at one of them, and that will cause light to kind of go through this fiber that we've got set up between the two cavities and then interact with the other Bose-Einstein condensate, and through that hopefully they'll become entangled.
We are investigating a system of a two-component Bose-Einstein condensate. Due to the differences in the interactions of these two condensates, there may be separation of them occurring at some point. We are trying to figure out how it will affect the quantum computing.
My name is Rie. I'm from Japan. I'm working at NII for looking after the intern students and the researchers who are coming to NII. Accidentally, I started working for this group. I hate physics, but since I started working for them, I became really interested in, not really, a little bit interested in physics. Sometimes they are really annoying, but basically they are very nice and very friendly, and I don't feel like working for them. I feel like just enjoying or having fun with them.